Let me show you a card trick. Take a standard deck of 52 cards and split it into 13 piles of 4, in any way you'd like. Done? Good. Now, I'm looking for a full run of all 13 ranks, from ace to king. After looking through all the piles, I decide to take exactly one card from each pile, such that I have my full run, ace, 2, 3, and so on, up to king. Let's try it again. Maybe that was lucky. Shuffle the deck and split it into 13 piles. Again, I'll pick one card from each pile. I can again do this in such a way that, in the end, I end up with a full run. Why can I always do this? In this video, we'll explore the mathematics of network flows. In trying to maximize flow through a network, we'll discover two quite important tools: the max flow min-cut theorem and the Ford Fulkerson algorithm. By modeling our card piles as a network in the right way, we'll use these tools to explain why our card trick always works. Let's imagine we have two cities, connected by some railway system. In the middle, there might be some stops, with trains running to and from those stops. Each train has some capacity, some maximum number of passengers it can carry per day. If we think about a specific route from the starting city to the ending one, say in this case the journey through Calais and Antwerp, the maximum number of passengers which can travel along that route each day is the minimum of all the train capacities along that route, since the flow of passengers will bottleneck at that leg of the journey. As they say, a train is only as strong as its weakest link. If you're a transportation planner, you might want to consider the following question. Using the entire network, what is the maximum number of passengers we can transport from the first city to the second in a day? This is known as the maximum flow problem, and it's the question we'll think about for the rest of this section. Before we get started, let's introduce a bit of terminology. In the railway system example, mathematicians would call each stop a vertex, and each train line an edge. We'll imagine that each train only runs one way, so that the edges are directed. A network is a collection of vertices and edges, with a marked starting vertex and a marked ending vertex, to which we wish to find the flow. What then is the maximum flow we can push through this network? Let's go back to the network we had before and take that as an example. This network has 7 vertices, with 0 being the starting vertex and 6 the terminal vertex. This time, let's have red edge labels represent the capacities of each edge, and white edge labels represent the actual flow going through the edge. Say we wanted to find the maximum flow through this network. We'll begin with no flow at all. We will then keep trying to increase the flow by as much as possible until we no longer can. Now, if there's no possible way to increase the flow, then we must have reached the maximum flow. This simple idea forms the basis of what's called the Ford Fulkerson algorithm. To increase the flow through the network, we need to find a path from the starting vertex to the terminal vertex where we can increase flow. This is called an augmenting path. Let's take this path. Now, there's two things we need to keep in mind before we increase the flow, namely our two constraints. Firstly, each edge can only have as much flow as its capacity, so whenever we increase the flow, we need to make sure we don't exceed the capacity of the edge. Secondly, we can't forget the conservation of flow. However much flow comes into a vertex must also leave it. For example, One thing we could do is increase the flow through each of the edges by 1. By doing this, we've increased the total flow of the network by 1. Notice that we had to increase the flow in all of the edges by the same amount because of the conservation of flow. In fact, looking at the capacities, we could have increased the flow by much more than 1. Even increasing the flow by as much as 6 would not violate any of our constraints. Any more, however, and we would exceed the capacity on the edge between vertices 1 and 4. Now, we've increased the flow as much as we can on the path through vertices 1 and 4. So let's look for another augmenting path. We can do exactly as we did before to the new path through vertices 2 and 5. This time, the most we can increase the flow by is 5. In general, we pick an augmenting path from the starting vertex to the terminal vertex. We then go through each edge in this path and calculate the difference between the capacity and the current flow. The minimum of these differences tells us the maximum amount we can increase the flow by without violating a capacity constraint. Now, let's just keep going with this. So, let's stop for a moment and see if we can find any more augmenting paths. After a moment's thought, you'll realize that there are no paths left where we can increase flow. In other words, we reached the maximum flow, which in this case is 19. What we've just described is a full run of the Ford Fulkerson algorithm. At the end of the algorithm, we are always guaranteed to have a maximum flow. That wasn't so bad, right? Notice that when all of our capacities are integers, then the flow at each step of the Ford Fulkerson algorithm is also an integer, meaning at each step our flow increases by some positive integer. This aspect will prove to be quite important when we come back to the cards problem. Let's think back to the maximum flow problem. If we simply want the value of a maximum flow, and don't need a specific example of how the value is achieved, for many networks, there's a slightly easier way of finding the maximum flow through the network. This result, called the max flow min-cut theorem, is what we will explore next. We now have an algorithm to find the maximum flow. Let's introduce a way to find the value of the maximum flow without running the entire algorithm. To do this, we'll think about making a cut in the network. Mathematically, a cut is a partition of the vertices into two parts, which we'll call S and T, where S is the half that contains the starting vertex, and T is the half that contains the ending vertex. The cut intersects all edges connecting vertices of S with vertices of T, and vice versa. We can think of a cut as a kind of cross-section of the flow. The net flow sent across any cut, counting both forward and backward flow, is equal to the total flow through the network. Thinking back to the train analogy, every passenger going from the starting vertex to the ending one has to eventually pass the cut a net total of 1 time. Let's define the capacity of a cut to be the sum of the capacities of the edges leaving S. That is, we count forward edges, but not backwards edges. Different cuts can have different capacities. For example, we can change our cut here by adding vertex 3 to S to reduce the capacity from 23 to 19. How does this relate to maximum flows? The maximum flow through a network must be the net flow through a cut at some point in time, so it can never be more than the capacity through any cut. In fact, though, the maximum flow through a network turns out to be always equal to the minimum possible cut capacity. In this case, our current cut turns out to be the minimum possible cut, so from this we deduce that the maximum flow is 19. So why can we always find the cut with capacity exactly equal to the maximum flow? Let's first run Ford Fulkerson on our network to find the maximum flow. The key is to define S as the set of vertices V such that we can find the path to V along which we can increase flow. For example, consider this path. Neither of the edges on this path are at maximum capacity, so this is a path along which we can increase flow. In other words, the vertex 1 is in S. Now, consider this path to 2. We can also increase the flow along this path by increasing the flow through the first edge by 1, and decreasing the flow through the second edge by 1. In general, we can increase the flow through a path if each forward edge is below maximum capacity and each backward edge has positive flow. With this definition, we find that vertices 0 to 3 are in S, but vertices 4 to 6 are not. We see that the ending vertex is always in T, since otherwise the flow we started with would not be maximal. Defined this way, what is the capacity of our cut? The cut cannot pass through an edge that isn't full, since then we could increase the flow to the endpoint of that edge by first increasing the flow to the start of the edge, which is in S, then increasing the flow through the edge. The cut also cannot pass through a backwards edge with flow, since we could do the same thing, increase the flow to the end of the edge in S, and use that to decrease the flow going through the backwards edge. This tells us that a cut only goes through forward edges, and these forward edges are at full capacity. Now remember the key fact we used before. The net flow through this cut is equal to the total flow through the network. Thus, the capacity of the cut must be exactly equal to the maximum flow capacity. We found our desired cut. This is the max cut min flow theorem. The maximum flow is exactly equal to the minimum cut. This allows us to convert a problem of flows into a problem of cuts. Now, we finally have all the tools we need to explain our card trick from the very beginning. Let's first remember what exactly happened in the card trick. We took a deck of 52 cards and split it into 13 piles of 4. No matter how we split the piles, we could always pick out one card from each pile to make a full run, from ace to king. What does this have to do with networks? Imagine lining up all the piles in a column, and opposite them, lining up all the ranks. Connect a pile to a rank if that pile contains that rank. If we want to select a card of each rank, we want to find a perfect pairing between the piles and ranks. That is, each pile should be connected to exactly one rank, with no two piles sharing the same rank. But how can we find this pairing? With flows. Let's make a starting vertex on the left with capacity 1 to each existing pile, and an ending vertex on the right with capacity 1 from each existing rank. So we know that the middle edges won't block our flow. Let's give them infinite capacity. What happens when we run Ford Fulkerson on this network? In each step, we pick one path to augment. That is, we connect a pile to a rank within that pile. Once a pile is picked, the edge leading to that pile is full, so the pile can no longer be picked again. On the other hand, once a rank is picked, the edge leading out of that rank is full, and so the rank can no longer be picked again. That is, at each step, the algorithm picks a pile and pairs it with a rank, in such a way that no two piles share the same rank. This is exactly what we need. If we can just show that the algorithm can run for all 13 steps, then we've gotten our perfect pairing. That is, we want to show that the maximum flow through the graph is at least 13. By the max cut min flow theorem, this is the same as showing that every cut on our graph has value at least 13. let's look at cuts. If we put a pile in S and connected rank in T, then our cut would have infinite capacity. Thus, to minimize the capacity of the cut, if a pile is in S, then all its connected ranks better be in S as well. If we pick any K piles to be in S, we've put a total of 4 K cards in S. There are only 4 cards of each rank, so these K piles must contain at least K ranks between them. All these K ranks must then also be in S. Now, each rank we put in S contributes exactly 1 to the cut, and each pile we put in T contributes exactly 1 to the cut. Let's say we pick K piles to be in S. Then, there are 13 minus K piles in T, and at least K ranks in S. So in total, the value of the cut must be at least 13 minus K plus K, which is at least 13. Since this works for any K, the minimum cut value is at least 13, and by taking K equals 0, we find the cut of exactly 13. Thus, there must be a flow of 13 through the cards, and hence a perfect pairing. In this video, we've explored the realm of network flows, an indispensable tool for making sense of and optimizing real-world systems. Along the way, we've transformed cities into nodes and railways into edges, whilst helping out a few transport ministers along the way. Of course, we couldn't have done this without the trusty Ford Fulkerson algorithm, a beacon of simplicity driving us towards flow value optimization. I hope you've enjoyed this video, and until next time, keep exploring.